Good day, ladies and gentlemen. Engineer Peter is back again. We'll be taking a tutorial on unsymmetrical bending. And today we have a very simple sample question. And the question says, the tension flange of a cast iron I-section beam is 240 mm wide and 50 mm deep. The compression flange is 100 mm and 20 mm deep, whereas the web is 300 mm by 30 mm. Find the load per meter run which can be carried over a 4-meter span by a simply supported beam if the maximum permissible stresses are 90 megapascal in compression and 24 megapascal in tension. Let's move straight to the solution. I'll be taking you step by step on how to solve questions like this. So firstly, as we always do, take out the parameters we're given. We're given the compressive stress, which is 90 megapascal, and the stress at tension is with 24 megapascal. So this is a diagram for the question. From the parameters given, you can easily draw it. You can see that the tension flange is at the bottom, 240 by 50. The compression flange is at the top, 100 by 20, all in mm. And the web, which is 300 by 30. So we're going to be taking 3 steps in solving this question. So the first step is to find the moment of inertia along the neutral axis. So to do that, first we must find the area of the section. So let's look at the section quickly. We can divide the section into 3 parts. We can divide it into 3 parts. Tension flange will be 1. The compression flange, and then the web. So we can see that the area of the section will become A sub 1 plus A sub 2 plus A sub 3. Once you can get A1, A2, A3 and add them together, we have found the total area of the I section. So A1 will be 100 times 20, which is the area of the compression flange. 100 times 20, which is length times breadth. 100 times 20 gives us 2000 millimeters squared. A2 is the area of the web, which is 300 times 30, which is 9000 millimeters squared. And A3 is the area of the tension flange, which is 240 times 50, which gives us 12,000 millimeter square. So total area will be 2000 plus 9000 plus 12,000, which gives us 23,000 millimeter squared. So y, we want to find y. Y is the farthest point from the neutral axis. Here we do not know the neutral axis at the moment, but we can find y to get where the neutral axis will be, since this section is unsymmetrical. So we use the relation y equal to a1y1 plus a2y2 plus a3y3 over a. from this shape, you can see that, like we said before, A1 is the compression flange, A2 is for the web, and 3 is for the tension flange. So A1 we already know. What will be Y1? Y1 will be the distance, the vertical distance between the ground AB and the midpoint of the compression flange. And we know that the depth of the compression flange is 20, so the midpoint will be 10. So you can see from the diagram to your right that Y1 has been determined as 360 because we have 50 plus 300 gives us 350 plus half, which is 10. That's 50 plus 300 plus 10 to give us 360. Y2, we are going to calculate from the half of the web, which is 150. And so half of the Y2 will be 50 plus 150, which is 200, as you can see from the diagram. And then Y3 will be just half of 50 because we are looking at from the ground to the middle of any particular section. So you can see now that we are putting our values. A1 we have determined as 2000 and Y1 is 360, like I just said. A2 we got as 9,000, Y2 as 200, A3 12,000, and Y3 25. So if you put that into an equation and divide by A, which is 23,000, we're going to arrive at 122.6 millimeter. So that's our farthest point from the neutral axis. That means from the bottom AB upwards, you are going to move 122.6 millimeter to arrive at the neutral axis. So this is the diagram as it is. So you can see that we have put our neutral axis XX, and from the bottom AB to that point XS has been designated 122.6 millimeters. Now, before we move forward, let me show you something. We are now trying to find the moment of inertia along AB. So, we're not going to take the 1, 2, 3 we used before designation. We're going to ensure that the maximum number of sections touch the AB axis. So to do that, we're going to cut the web through, cut it through to touch the AB axis. And so we now have a shape as P, Q, and R. P, which is the tension flange, has been divided into 2 equal parts by the web. We want the web to touch the AB axis. And so once we cut it to touch, we now say PP to show that that is P, although it is P, but it is now divided into 2 by the web. And then the Q is touched. So we have 2 sections touching the axis from which we want to find the moment of inertia. We have P touching, Q touching, only R not touch. So out of the 3, we have 2 touching, and this is very good and it makes it simpler. So IAB, which is the moment of inertia along the AB axis, will be divided into 3 parts since we have 3 sections already, P, Q, and R. So for P, it will be BD cube over 3. These are standards. For Q, it will be BD cube over 3. But for R, since R is not touching the AB axis, we're going to do a little adjustment. It's going to be BD cube over 12 plus ARYR squared. I take it again. IAB is equal to BD cube over 3 for P, BD cube over 3 for Q, and BD cube over 12 plus ARYR squared for R, since it is not touching the AB axis. So from this, we can calculate our B. For P, which is the tension flange, we know that AB is 240, but since we have cut off the web, the web was given as 30 mm thick. So note that B for P will not be 240, it will be 240 minus 30. And then for D, we already know D is 50. And then for B is 30, we already know. But the D has been extended by 50 mm since it cut through P to touch AB. So that D for Q will be the original length given 300 plus 50. And then for R, there's no cutting. B will be 100, D will be 20. And then let's move on. So this is the question we have. So this is the diagram we use to get our equations. This is the diagram for cutting our shapes. And so when we put our values, we see that IB becomes 240 minus 30 for B. D is 50 cubed, like I said. And then for Q, B is 30, D is 300 plus 50. And then for R, B is 100, D is 20. And then A, I've calculated A for R before as 100 times 20, which is 2000 times 360 square. I've calculated this one before. It is from the ground to the center of R. That's the distance between R and the axis we are using. So if you simplify this, we arrive at 696.77 times 10 raised to 6 millimeter raised to power 4. What we have just calculated for is the moment of inertia along the AB axis. But what we actually want is the moment of inertia along the neutral axis, that is IXX. So to get ISS, we use the relation from the parallel axis theorem. IXS is equal to IAB minus AY squared. We use this relation to get the moment of inertia along the neutral axis SS. We already know our value for IAB to be 696.77 times 10 raised to 6 millimeter to power 4. We already know our A as 23,000 millimeters squared. And we just got Y as 122.6 millimeters. So if we put these parameters into the equation, ISS equal to IAB minus AY squared, this is what we arrive at. We arrive at 351.06 times 10 raised to 6 millimeter raised to power 4. What we have now is a value for the moment of inertia along the neutral axis. 351.06 times 10 raised to 6 millimeter to power 4. So the next step, we're going to find the moment of resistance. First, before we do that, we must first test what we were given. We were given two values, if you recall from the equation, sigma C and sigma T. Permissible stresses in compression, sigma C, and permissible stress in tension, sigma T. Now, this expression is used to test if we are within the safe range. So now we assume that the tension is at maximum. It could have been the compression, does not matter. So we're testing the tension to see if the compression is within the range. You want to test, can test compression to see if tension is within the, but for this question, we're testing tension. We're putting the value for tension to see if compression is within the safe range. Sigma T is 24. Y sub T, which is from the bottom, what we calculated before, is 122.6 millimeter. So this is the value. So YT is 122.6 millimeter. YC will be the remaining part, which is 247. That's the whole length minus 122.6, which is 247.4 millimeter. So if you put that in the equation, YC over 24 is equal to, sigma C over 24 is equal to YC, which is 370 minus 122.6 over YT, which is 122.6. If you solve for sigma C here, you arrive at 48.43. This is safe, since what was given was actually 90 megapascal. So we are within the safe range. That means we can go ahead. So the moment of resistance, we're using the relation M sub arrow equal to sigma I over Y. I there is the moment of inertia along the neutral axis. So we see our figures. Sigma T is 24, Y sub T is 122.6 millimeter, and our ISS, which is our moment of inertia along the neutral axis, we have calculated before as 351.06 times 10⁻⁶ millimeter raised to power 4. So if you put our values into that equation and simplify, we'll get our moment of resistance as 68.72 times 10⁻⁶ Newton millimeters. So the third and final step, we're now going to calculate for the uniformly distributed load. So we're using the relation maximum bending moment M equal to WL squared over 8 for a simply supported beam. Maximum bending moment M is equal to WL squared over 8. And we know that L was given to us as 4 in the question. And so W there stands for the load. We are putting a letter since we do not know the load. You could have used any letter, but permit me to use W, where W is the load, L is the length given. It says 4 meter span. So if you put it into our equation, you see that M equal to W times 4 squared over 8, which is 2W Newton meter. We're arriving at meter because L was given to us as meters. So we convert to millimeter by multiplying by 1000. So it gives us 2000 W Newton millimeter. So 2000 W is our maximum bending moment. And we already know that maximum bending moment is equal to our moment of resistance. So we equate the two. Maximum bending moment is equal to the moment of resistance we just calculated not a while ago. So 2000 W equal to 8.72 times 10⁻⁶. So we get W by dividing through by 2000. So our final answer becomes 34360 Newton per meter, or can convert to kilonewton to make it smaller, which is 34.36 kilonewton per millimeter. So this is the load per meter run that can be carried over by 4 meter span simply supported beam. So this is the final answer to our question. Now, if they say the tension flange is 200 mm wide and 40 mm deep, compression flange is 80 mm wide and 20 mm deep, and the web is 240 mm by 24 mm. These are just variations. You can go the same step. We could do another practice question. Find the loads per meter run which can be carried over an 8 meter span by a simply supported beam. Now, let's say the question is the same, but the span was increased to 8 meters. What do you think will happen to our answers? Same thing, just that in the place where you have m equal to ws squared over 8, in the place of l, you put 8 and not 4. And then, lastly, for this tutorial, assuming you were given the maximum permissible stresses as 120 megapascal in compression and 45 megapascal in tension. Same thing, just that your sigma C is now 120 megapascal and your sigma T is 45 megapascal. That is, take it again, your sigma C is 120 megapascal while your sigma T is 45 megapascal. Clear.